Hi, welcome to the Signal Path. In this episode, we're going to attempt another repair. This is an Agilent 3458A. It's actually been a long time since we've done a repair on one of these units, and the price of these continues to climb. So they're definitely worthwhile attempting to repair. So let's turn this one on. It does turn on. The screen looks reasonably okay. Then it runs a checksum, and then it's going to go through some testing of hardware. And I think it does generate an error. Let's see what error pops up. There you go. So there is an error in there. So if I go over and look at the error, you can see that it's asking that we should perform an ACAL. And that's most likely because either ACAL hasn't been run or something's happened or the last time it's failed. So therefore, we should be able to go back and perform an ACAL and see what happens. There we go. Now let it run. This is going to take a little bit of time. So we went through the voltage calibration, but then as soon as it hit the resistance calibration, it immediately generated an error. So if I go and look at the error in this case, it says error 209, hardware failure. That's not good. And then internal overload 104. Okay, is that the only one? And then there is error 210, internal hardware failure again. Yes, there we go. Yes, calibration required. We know that one. Any more? Calibration error. Okay, anything else? System error. Oh, non-volatile RAM checksum. Okay, so that means that the battery on the unit has also run out. So there's multiple problems in here. There you go, all the errors are gone. So I think we should fix that battery problem for sure, because otherwise we're going to run into other issues. But the problem with the internal measurement, that's a bigger problem. Now before we dig into it too much, let's see if it measures voltage correctly, because it did pass the voltage calibration test. So I have it directly connected to the Fluke 754, which is a process calibrator. We can synthesize voltages, currents, and resistances with this pretty accurately and precisely. So right now it's set to 0 volts, and this is measuring roughly 0 volt, which is a good sign. Let's try 1 volt, for example. 1 volt, and yeah, look at that. That's pretty good, I would say. It's reasonably close, and some of the calibration may be off, of course, but nonetheless, it seems to be measuring voltage correctly. So here's 5 volts, and 5 volt looks good as well. Let's try 10 volt, and 10 volt looks good. Yeah, that's pretty good. Let's try something small, 10 millivolt, and it should measure. There you go, 10 millivolt, very good. 1 millivolt. And that's also 1 millivolt. So the voltage definitely works. We can also test the current, which hopefully should be based on roughly the same circuitry, and see if that works. So let's try 1 milliamp over here now. Yeah, that's quite a bit off. That is a little bit concerning. Let's try 10 milliamp. And yeah, oh yeah, that's way off. So there's something going on there. Perhaps there's something more than just the ohms measurements, or there's some overlap in the circuitry that's at fault, but this is way out of range. So the AC voltage is also a little bit off. It should be 0.353, but we're reading 0.36, and this is a 1 volt peak-to-peak signal that I'm feeding into it, so that perhaps the problem is more widespread, or maybe this is just really out of calibration. The last thing we should try is the resistance. Now the resistance did fail, so I don't expect it really to work, but we should try that anyway. And here we are trying to synthesize a 1 kilo ohm resistor, and it's reading 25 kilo ohms, so it's way off. And that's not surprising. We know that that is filled. Let's try 1 ohm, pretty small resistance, and then, yeah, it's reading 14 ohm. Yep, completely broken. All right, now time to dig into the actual circuit architecture. And luckily, there's a lot of information available that we can dig into and see if we can understand the problem. So this is the overall block diagram of this instrument. This is obviously looking at it from a very high level, but we should be able to deduce some information. So here's the inputs coming into the unit. And then we have something called an input switching and signal conditioning. This entire board, which is the A2 board, I believe, is floating, and therefore it is isolated from the rest of the instrument because of the sensitivity of everything that's on here. Now, I don't think there is a problem here, because if there were, we wouldn't be able to make any measurements, or at least we wouldn't be able to make the voltage measurements very well. There's also power supplies, which I'm assuming are working, and if you look at this, there is indeed an ohm current source and AutoCal section. And this is a section that presumably goes through the calibration routine to try and figure out what the ohms ranges should be, and so on. Now, most instruments, most multimeters, measure ohms in exactly the same way. They have to supply a precision current, and then they have to make a precision voltage measurement. And those two compound the precision gives you a good idea of what your unknown is. The resistance is just simply Ohm's law. The challenge here is to create the appropriate currents based on the same reference as the voltage reference done, so that you can make these correlated measurements. And I think that's what this section is doing. And there's the DC auto ranging, current ranging, and so on. We probably don't have to worry about these so much at the moment, and this is where we should focus. So you can see the reference feeds obviously data converter, as well as everything that goes into all of these internal auto calibration measurements, because they all have to be based on essentially the same reference, aside from having precision resistors and so on built in. the logic circuitry and so on over here obviously is working because the instrument is powering on. It does, however, have somewhere on here the places where the SRAM is storing calibration and user data, and I think that second error that we saw is from this. We'll have to take a look at that later. But we can bring up the schematic of this portion. The schematic of the entire instrument is enormous. There's a lot of stuff there, but we can focus at least on this part. So the 3458A has a very good resistance range measurement capability. When it is set to a 10 ohm range, it can measure resolutions down to 10 microohm thanks to its very high resolution internal A to D converter. And part of the reason for that is because when you're measuring a very small resistance, it pushes a fairly high current through it, 10 milliamp. Now 10 milliamp to 10 ohm is 100 millivolt, and that's more than enough to achieve this resolution of 10 microohm. But when you're doing a 1 gigaohm measurement range, you obviously cannot move 10 milliamp through that resistor anymore. You will have an enormous voltage. In that situation, the current is reduced to 500 nanoamp. And the instrument will dynamically change this current, and that's what auto ranging is. And how fast it can jump between these is the auto ranging speed, which you can measure on any multimeter, and it's something that people desire because if you're moving around a circuit, you want to quickly settle. So the way the settling works depends on the internal algorithm, but it shouldn't be too difficult. It will start from a certain current, it will measure the voltage. If it's over a certain range, then it will downscale into a smaller and smaller current until it gets the voltage it expects across the device. You can also force the range in a specific area and keep it there by removing the instrument from auto ranging, and that can push a specific current that doesn't jump around anymore. And sometimes it's advantageous, particularly at areas where it's really close to the transition between two of these ranges and there's an overlap in there. So if you look here at the bottom, for the 10 meg, 100 meg, and 1 gigaohm range, it uses 500 nanoamps, so it keeps that constant, and it increases it as you go higher and higher. So we should be able to take a look at this and measure that. The reason I'm focusing on this part first is because that auto calibration routine must go through all of these ranges and compare the measurements via some internal known states so that it knows that it is actually working and it can zero and take care of all the various offsets that it may have internally. So this could be a problem, and that overload condition could indicate that something's gone wrong and it's overloading the ADC as a result of it. So we should really go and find where the schematic is that does this in the circuit. And among the many, many pages of schematic, I have found the area responsible for this ranging of the ohms measurement. And I know we're looking at it from a very high level here, but I will zoom in a second. But from the top level, I can see that there are different range currents. So there is one here that's 0.5 microamp. That's the 500 nanoamp range. Here's the 5 microamp range, 50 microamp, 100 microamp, 1 milliamp, and then finally 10 milliamp. So these switches are controlled with this batch of comparators, and these batch of comparators enable various amounts of these currents to be switched, and there's some precision resistors over here that ultimately set those currents. It looks like some kind of a shift register maybe here that controls all of this. And then the output of all of them are summed on this line that you can see connects all of them all the way through, and then they end up in this op amp, the U300, whatever that is, and that should be in some kind of a feedback configuration. Now we should zoom in a little bit more now because I think that it's probably quite hard to see. Let's see if I zoom in here. I should be able to pan this now. Here we go. So there's a part of the schematic here I think is a little bit washed out. Now if you look at this, this amplifier must be in negative feedback in order for it to obviously be working correctly. So there is a capacitor here, most likely for stabilization of this op amp. So if I were to redraw the missing part and maintain a negative feedback, I think it has to be something like this. If I'm not mistaken, there's a resistor in here. Yeah, this way we have the output over here, and then yeah, that creates the feedback between this. So yeah, so this op amp obviously has to work, otherwise nothing works. And then afterwards, we have a whole bunch of switches here. There's some resistors there, perhaps some precision resistor, and this is all guarded, as you can see. I'm just looking at it on top of my head over here, and then it goes that way. So let's forget about that for a second. We should be able to do a couple of really preliminary tests. We can go and look at all of these points and see if they're switching. And if yeah, these are actually digital switches. Yeah, so this connects to this connects to this connects to that. So we do have some voltages in here. This should be digital. We should be able to measure this. We can even start from here if you want to. So as we change the range manually, we expect various signals to appear at the input of these ICs, which then change the output, and these outputs then switch these MOSFETs, these JFETs probably, and then that's how the switching is done. So we have several things in a row that need to work. This op amp needs to work, all this feedback needs to work, these transistors need to work, these FETs must all be functional, this current setting must be correct, these U304s, which are LP385s, I guess some kind of a comparator, they must work, and this must work. And here's a top view of the 3458A. with the top cover removed. And as always, it is a beautiful instrument. This is typically covered, which we have removed. And if you notice, you can see that this top piece is held together with these plastic spacers because the entire thing is floating, and you can see the bias voltage is being applied to the different plates. So you got to be careful working on these things. So this one does have the at least one of the later versions of the digital board with these batteries, which most likely are dead. There's another reason why I really want to fix this, because it is the modern version of this, which is quite a bit better, at least from the digital side. And then we have a reference voltage over here. And if I look carefully, based on some of the marking, this area roughly is the area where we have that place where the ohms measurement is done. Look at all these big beautiful relays. There are some precision resistors which are at an angle. I have to resist the urge to straighten them out because you don't want to touch them. You don't want to create that strain afterwards on them. Yeah, it looks pretty good. So let's focus a bit more here and see if we can identify the elements of that schematic. So I think I found most of those components over here zoomed in. So here's that connector you were seeing the end of when you were looking at it from the top, and here's a corner of the reference board. So here's that op-amp U300. It's a burp round part. I really hope this is not dead, because I don't know if I can ever find a replacement for this one. This must be that weird package device with all the resistors and devices inside of it. We have this one and this one. These are our two comparator banks that control the FETs. Here are the FETs, so different ranges. I think starting from here, you can see 1, 2, 3, 4, 5, 6 of them. They are the ones that need to switch to provide the appropriate current. This guy, I believe, controls these comparators, and the rest I don't think are related. A few other resistors and so on. So we have everything we need to start doing some measurements over here. And just to make sure we're not missing anything, so we have 1, 2, 3, 4, 5, 6 unique current source ranges, and we do have 1, 2, 3, 4, 5, 6 of these FETs. So it all lines up. So an easy thing to measure is the current coming out of the multimeter, so we can see what those ohm current ranges actually look like from the outside. So we're going to use this meter to measure it. I basically have it connected to the current input, and we're going to measure the current going through the unit. Sorry about the flickering, that has to do with the weird OLED display of this particular meter. So I'm going to switch the meter to DC ohm measurement, and let's see what do we get. Ooh, 10.4 milliamp. That's actually quite high. That's higher than the 10 milliamp it should be. This is an auto ranging mode now. So I'm going to change the range. I'm going to go all the way to the smallest range first. So here we go. This is the smallest range. So here it should be doing 10 milliamp, and it's clearly not doing 10 milliamp. That's a problem. So let's increase the range. 1, 2, 3. Okay, it changed a little bit. 4, 5, 6, 7, and now we're at gigaohm. And now it's at 10.1. So that completely explains everything. The current isn't shifting. Right now, the current should be 500 nanoamp. It's definitely not that. So let's go all the way back down again. So here's the ohms measurement. Let's null this out. And let's see what do we get. Okay, so now it's going to measure the delta. And let's now change the range again. Go up. Nothing, nothing, nothing. And that's actually consistent. For the first two, nothing happens because the current isn't supposed to change. But then we do get a little bit. So there's something is working. There you go. It increased again. Yeah, okay, that makes sense. So there's some changes. So perhaps not all of it is damaged, but there's certainly a problem. And if I go back all the way down, it goes back to where it was. So it's repeatable, but it's not the right value. So that kind of tells us everything we need to know about the fact that why that error in the AutoCal is happening, because that entire current ranging is broken. So let's do a really quick test on this burp round op-amp here, the U300, and let's just see if it's damaged or not. We may not be able to tell 100% if it's fully functional, but we can tell if there is something immediately wrong with it. Now in the schematic it says that this should have an 18 volt power supply, which over here is the pin number 7. So I should be able to measure that. Let's see if it does have its power supply. There you go, 18 volts. Okay, it does have a good power supply. Now let's make sure its two inputs are roughly at the same voltage, meaning that it is in negative feedback. So that's those two pins over there. We should be able to easily measure that. So here's one of them. So in plus is at 9.72. In minus 9.72. That's good. That is promising. Let's make sure its output is not saturated, which is the pin right next to the power supply pin. 11.94. Good. So with a power supply of 18 volts, it is not saturated. These are all pretty good signs. It doesn't mean 100% that it is working. It's not hard or anything, but at least it is seems like it is in negative feedback and it is regulated correctly. So that allows us to move further back into the chain and try something earlier. So next we can take a look at the gate of these FETs to make sure that these gate signals are appearing and disappearing as we change the range manually. So all those switches are there. They're organized in gate, source, drain configuration there on the PCB. So I'm going to start from the lowest one, which is this 500 nanoamp one. So if I measure the gate over here and I set the range to the highest range, the gigaohm range, I should see a signal here because this path should be enabled. But as I increase it, eventually that signal should disappear once I'm 3 ranges up, because this is no longer relevant, it has to jump to the next one. So that's a quick and easy thing we can try. So here I'm measuring the gate voltage on the lowest current, which is the highest range over here, and I'm going to go and step back. Eventually, after changing the range 3 times, I should have that signal disappear, hopefully. So there we go. So as 1, it should stay. 1 more time, it should stay. And now, there you go, look at that. It does disappear. And now the next range is the 5 microamp range. That one should be enabled. And it is enabled. Good. Now if I change the range 1 more time, that one should disappear. And it does disappear. Good. Now the next one. This is now the 50. It should disappear with 1 click. And it does. Very good. Now the 100 microamp range. And that one is it there? That is there as well. Now that should disappear too with 1 click. And it does. Well, all of them seem to be working. So what's going on here? We have the 1 milliamp and the 10 milliamp, and those are probably the most suspect. Just have to find the right pin to probe on that one. Is this one enabled? This I think is the 1 milliamp. Yeah. Okay, I had to change my hand over there. There we go. Let me step down. It didn't change. That is interesting. Okay, now it shouldn't change 1 more time. And then the last one, it changed a little bit. Okay, there you go. That explains a lot. So the 1 milliamp one is not switching. Okay, that is a lot of useful information. Now we can try also the 10 milliamp range. Let's see if that one is on as well. That one's also on, and it shouldn't be on. Okay, so that limits the problem to these 2 ranges, and it makes sense because we do have the 10 milliamp. So now we can focus further on here and see what's going on. The signal on these FETs are there, which means we need to step 1 further back and find out where that signal is coming from, and if that explains the problem. So looking back here at the schematic, we can see that we verified the 500 nanoamp current does turn on and off. That one's okay. The 5 microamp signal was okay. 50 was okay. 100 was okay. But then once we got into the 1 milliamp and the 10 milliamp, these signals were not okay. And that could explain the excessive overload condition and the excessive current in the ohms range as well quite nicely. Now something else also pops out that's worth noticing. And if you look at all these signals from the 500 microamp all the way to the 100 microamp, they're all supplied by U304. So you can see U304 is used multiple times. And these signals were all okay. But as soon as we hit the 1 milliamp and the 10 milliamp range, they're actually supplied by a different IC, the U303. And that IC is also involved in the overload and auto-ranging condition. So that's interesting. These are 2 different chips providing these batch of signals, and that's helpful. Certainly points more towards U303 being an issue. Now you may also ask, well, how do we know that this U307 is not the problem? Well, what are the odds that the outputs of this are all working on U304, but all of a sudden they're not working on the U303? So it's much more likely that the U303 is the problem, whatever this comparator chip is, and there's 2 of them obviously inside the circuit, and they're identical. It is possible that some other things are bad, like these resistors, but I would suspect this to be the first cause. But we can go a step back and measure the input and output of this and certainly compare them with the one that supposedly is working. So I went ahead and installed these extenders on these 2 chips. This is supposedly the good one, the one that controls the lower ranges, and this is the one that doesn't seem to switch when the high ranges are supposed to change. We've basically looked at the output of these. Those are the inputs of the MOSFETs we just measured. It's the inputs now that I want to look at to make sure that they're arriving correctly at these 2, and also to double check and find out what ranges those inputs are supposed to have. So here's the input on the good IC, the one that controls the 100 microamp. So right now it's 5 volts, and then if I change the range, it goes to 0. So indeed it goes between 0 and 5, which makes sense. That's a logic circuit. So that's what the input's supposed to look like, and looks good, and the output certainly looks good. Now it's time to check this one for the 1 milliamp and 10 milliamp range. So here's the input to the 1 milliamp range, and this 0 volt is right. And look at that, 1.65, so it never reaches 5 volts. So I wonder if that's because it's clamping the output of that driver, the one, the shift register that's supposed to control it, because it only goes between 0 and 1.6, and it explains why its output is never changing, because the input is so small. So what does that mean? Well, it's either damaged, so the input is loading that driver, which is not able to drive it to where it's supposed to go, or maybe that driver's 2 channels are dead. Again, that's not very likely. So given that we're this far into this, I think I should remove this board, remove all those 3 ICs and put a socket in its place. That way we can quickly change them and swap them, especially swapping these two, and see if that fixes the problem, at least on some of the ranges, and then we'll have to look for replacement parts. So I went ahead, took out the board, and installed some sockets on these 3 components. I also swapped these comparators with each other. This is of course not going to fix the instrument, but it's going to point out if there are any differences between them, and the amount of current we're seeing in the ohm range now would change if they're not indeed the same, and they should be. I also didn't really show the soldering part. People often ask, but that's really most out of respect for the viewers, because there's so many views about soldering. Really don't need another one, especially a trivial thing like this. If there's something complex, I'll be sure to show it. Okay, let's switch the instrument to ohms and see how much current in 6. It used to be 10.4 milliamp. And what do we have? 1 milliamp. There you go. That's a difference that I was looking for. So definitely there's something difference between those two comparators, and there shouldn't be a difference, and that's a good indication. Let's look for a replacement now. And it's a few days later. I managed to find some replacements from eBay, $10 a piece, which is a lot for something like this, but they're quite obsolete. I changed them both so that they will be the same vintage. I intend to change this one as well. That one hasn't arrived yet, just so that because it's been driving something, its output was dragged down so that it is also refreshed. But for now, we should be able to do some tests. Okay, now for the moment of truth, let's see if these currents have been fixed. I'll put in the ohms range, and let's see what we get. Okay, 0.97, that's a little bit less than a milliamp it should be, but it may need some calibration. So let's go all the way to the lowest range there. So here, what do we get? There it is, 9.7 milliamp. That's pretty good. So at some point, it should be about 1 milliamp. That's correct. Let's see the next range. Oh, I think I may have passed it. There it is, 100 microamp. That's correct. Let's see what the next. There's a 50 microamp range. There is the 4 microamp, or should be 5 microamp range. And here's the 500 nanoamp. Okay, so they're all pretty close to where they should be right now. I don't know if there's another fault because they're a bit low, but it could be just needing an ACAL. Let's run the ACAL again. Okay, we run ACAL again, same as before, and let's see if it passes through the resistance now. And check it out, it passed the ohms self-calibration, it passed some DCI current calibration, so it's looking good. It's doing something at the end in the AC mode, and let's see if it finishes. Well, it finished, didn't give any more error. There's this error still here, but I think that's the non-volatile memory. I think it says, yeah, it says calibration required, which I just did, so probably have to restart it. Let me see what happens if I turn it on and off. Yep, that error completely gone away, so now it is running without any errors. I'm still a little bit worried about that non-volatile memory. I'm not sure why it does no longer showing the error. I think we should still address that. So before we test the unit fully, we should replace these 2 batteries with 2 new ones. These are basically battery backups on a pair of SRAM chips that are underneath them, and you can just remove these and snap another one into it, and they preserve the memory. These things have many, many years of life, both shelf and when they're installed. Now I don't know which one of these is dead. One of them certainly is. Now you have to be careful and replace these when the unit is turned on, because if you want to preserve the calibration memory, that's the only way to do it, because the SRAM needs to be powered. If you remove this, you lose all the data. I don't know if I've already lost my data because these things are obviously dead, or at least one of them is, but nevertheless we should change them. Okay, this is done. Let's measure the batteries inside of the ones I took out of the unit to see how well they were preserving charge. I know one of them is for sure dead. So here's the first one, 2.8. So this one's actually okay. Let's hope that this was on the calibration chip. And this other one, yeah, this one's dead, 0.42. So I'm going to throw both of these away anyway and make sure you recycle them. But these 2 new ones should be good for many, many years. And while we're at it, we should take a look at the IC that has failed and extract the die so we can look at it at the microscope. And that's exactly what I've done. And this IC has 4 comparators in it. So we should see some symmetry inside of this layout. And in fact, we do. You can see that we have this area over here, and this area over here, this area over here, and this one over here. They're identical because there's 4 individual comparators. And we should have 2 inputs going into identical devices, bipolar inputs in this case. And we can see that very well as well. We can see these 2, and then these 2 inputs, these 2 inputs, and then these 2 inputs are also identical. And we should have 4 outputs with a big diode on them based on the schematic of the circuit. You can see 1, 2, 3, and 4. So yeah, it's got a nice symmetry in there. The rest of the pins are I sets and V plus and V minus, but the layout is quite nice. We can look at it a little bit closer, but it's a basic bipolar technology, it looks like. And by looking at this, it seems like it has 6 layers of metallization. I wonder who makes this. Maybe it must be a really old technology because it's the one that was failed inside of the unit, but it must be some local foundry. Foundry may not even exist anymore at this point. But this is not the one that has failed. I don't know actually which one it was because I just randomly picked one. And these discolorations you see are the result of the acid eating away. I don't think this is a result of the part actually having failed, although it is possible, but it's unlikely. These pads have completely lost all of metallization because they were not covered, and so the acid ate away all the metal, and if you leave it long enough it will creep into the other layers and begin to eating other layers as well. I think that's probably what has happened here. But I think it might be a cool thing that whenever a component fails in the future, we should always just extract the IC and take a look at it anyway. It's an excuse to see something that we haven't seen before. And by applying differential interference contrast to the microscope image, we can reveal some of the lower level features, showing you the kind of non-evenness of the substrate and bring out the transistors a little bit more. So we can go through the prism settings, and here you can see quite a bit better how this is not completely planar in different places, and you can see the contacts of the transistors quite a bit better. If I go a little bit further, on the other side we get the relief now on the opposite angle eventually. There you go, it looks really nice now. You can clearly see where the transistors and the contacts and individual things are throughout the circuit. It looks really neat. It makes a cool wallpaper. So I've let the unit warm up for some time so we can run another ACAL on it. I'm also running another ACAL here on the Keysight 3458A at the bottom so we can do some relative measurements in case that is required. And then we can do a quick performance verification using, for example, the 5450A for resistance measurement. I have a couple of other units for precision, voltage, and current, and hopefully it will be back up and running. Okay, let's give it a try. Now, these are not the greatest cables. I am making a 4-wire resistance measurement. So let's set it up to 4-wire right here. Let's see what it says. Should be 0. Look at that. I would say that's pretty close to 0, and that's the value it's supposed to be. So let's go to 1 ohm. There it is. So let's see what we get with 1 ohm. Let's let it stabilize. Yeah, pretty close. 99972 should be 999695. I would say that's pretty amazing. Let's go to 10 ohm. What we get? 10 ohm, no problem. And let's go a little bit higher. Just 1 kilo ohm. 1 kilo ohm is really close there. Yeah, it's a little bit off. Let's try 10 kilo ohm. There you go, measures 10 kilo ohm without any issues. 100 kilo ohm. This is going through all the ranges of the ohms. That's what really is important here. 1 mega ohm. Let's say there it is. That is really close. There's 10 mega ohm. We should have no problem measuring that with this instrument. And finally 100 mega ohm. That's going to put us into the highest range. 100 mega ohm. Yeah, I think the resistance is working quite nicely. This is a 4-wire measurement. We can also do a 2-wire measurement, but it shouldn't matter at this 100 mega ohm range, of course. There it is. You can settle it down. But if I go to 1 ohm, that will make a difference. You can see it should be over 1. There it is, 1.25. But if I enable the 2-wire compensation, this value will change. Now I should match this more closely, and it's pretty close. I think the calibration probably wasn't lost. It looks promising. For precision voltage measurements, I'm going to use the Cronheit Model 523. I actually recently bought this from eBay specifically for another video I'm working on precision ratio generation with Kelvin dividers and so on. I think you would really like that, so make sure you subscribe, you don't miss that. For now, we're just going to use it as a source. And here's 1 volt, no problem at all, pretty close. Let's try 10 volt. You should no issues at all. And 100 volt for the upper ranges. 100 volt, I think this thing only goes up to 120 or so, but we can go down about 100 millivolt. Should also be no problem. Perfect. And 10 millivolt. 10 millivolt, very good. And then 1 millivolt. Nice. And then for just completion, how about 0.1 millivolt? Should be 100 microvolt, should have no problem. Yeah, it measures, no issues. And we can measure DC current in exactly the same way. Here I'm generating 1 microamp, and you can see that we're measuring it reasonably okay. Again, the cable setting isn't perfect, but it certainly can measure without issues. So let's try 1 milliamp. I'm going to have to go to auto range here for that. Should measure, look at that, 1 milliamp, no problem at all. And here is 10 milliamp. And finally 100 milliamp. We can try that too. For completion, yeah, I think the current measurement is now actually accurate. If you remember, it was a little bit off now, but I think it's working. Now, if you recall, the AC voltage was having a problem, but it is now correct. So 1 volt peak to peak does become 0.353 volt RMS. I think I should be able to do 10 volts as well. Whoops, that's not what I wanted to do. Here is 10 volt. It should be 10 times larger than that, almost exactly 10 times. There it is. Yeah, there you go. So I think it works too. And there you have it. I hope you enjoyed this. Thanks again to my Patreon supporters. You can also support the channel through PayPal. All the links are in the description. I really appreciate your support. Instrumentation has become quite a bit more expensive, so difficult to get a hold of these things and repair them. But I think there's a lot to learn, and I'll have a lot of the future videos in the queue for you. See you next time.